In this video, I will explain operation of stable multivibrator using IC555 timer. Here in this rescue diagram, two comparators are used here, comparator 1 and comparator 2, SR flip-flop, discharge transistor, and two resistances RA/RB and one capacitor. Comparator 1 is called as threshold comparator. Threshold comparator are also called as non-inverting comparator or non-inverting comparator. Non-inverting comparator. Why it is non-inverting comparator? Because the threshold voltage is connected to non-inverting terminal of the comparator 1. Okay, coming to comparator 2. Comparator 2 is called as inverting comparator. Inverting comparator. Because the trigger signal is connected to inverting terminal of the comparator 2. It is also called as or trigger comparator. It is also called as trigger comparator. This is the SR flip-flop. This one is the SR flip-flop. Control the operation of the stable multivibrator using IC555. This is the discharge transistor QD. Two resistances RA, RB, and C. The capacitor is charged through resistances RA, RB. These are the solid lines indicated here. The capacitor is discharged through RB. The capacitor is discharged through RB. The discharge indication is shown in this figure as dashed arrows. The capacitor is discharged through this QD transistor, discharge transistor. Operation. The output of the here V out is low. Here V out is low. Q is low. Q dash is not Q. V out means Q dash. Q dash is low. Q is high. This one is a NPN transistor. Whenever this Q value is high, that high value is directly connected to P terminal of the NPN transistor. Therefore, the transistor is driven into saturation mode. Therefore, the output at a seventh pin is 0.4 volts. 0.4 volts because the collector of this discharge transistor is connected to seventh pin of that 555 timer IC. Whenever the transistor is driven into saturation mode, the output at seventh pin is 0.4 volts. Here in between ground and 0.4 volts, two elements are there, that is resistance RB and capacitor is C. Already the capacitor having some charge. Therefore, due to this condition, the capacitor is discharged through transistor shown in figure. Therefore, the capacitor is discharges like that. The capacitor is discharges up to 1/3 VCC. The capacitor voltage here is called as a discharge like that. The capacitor voltage is nothing but the trigger voltage. Here, two reference voltages are there, 2/3 VCC here, 1/3 VCC. These are the 2 points. The capacitor voltage is discharged towards 1/3 VCC. That is nothing but trigger voltage. This trigger voltage is less than the 1/3 VCC. This trigger voltage less than 1/3 VCC. 1/3 VCC is nothing but reference level of the comparator 2. Therefore, it is at a high level. 1/3 is at high level. Therefore, the output of the comparator is high. The output of the comparator 2 is high. Therefore, R is high. Q dash is also Q dash is also high. Q dash is also high. That means here the Q dash is high. Q dash is high. Whenever the Q dash is high, Q is low. Q is low. Q is low means the transistor is in cutoff mode, driven into cutoff mode because here positive, here low value. That low value is insufficient to drive the transistor in saturation mode. Therefore, the transistor is in cutoff mode. Cutoff mode means the collector terminal is disconnected from that seventh pin. In that scenario, the capacitor is charged like that. The capacitor is charged here towards VCC. The capacitor charged towards VCC because VCC, RA and RB is connected to capacitor. Therefore, the capacitor is charged towards VCC. The indication is like that, solid arrows. Whenever the capacitor voltage is reached to two-third VCC, that means here two-third VCC. The two-third VCC is nothing but the threshold voltage. The threshold voltage, two-third VCC, is compared with the reference level. That is a two-third VCC reference level. Whenever that capacitor voltage crosses, that is nothing but threshold voltage, crosses this reference voltage, two-third VCC, two-third VCC. Therefore, the output of the comparator is high. Q is high. At that instant, up to charging here, the output is maintained like that. The output is maintained like that during that constant period, charging period of the capacitor. Okay, this is the one. Q is one. QD is driven into saturation mode. Here 0.4 volts and 0, in between 0.4 and 0, capacitor C and RB is there. The capacitor is discharges. The path is shown in figure here. The capacitor is discharges. Whenever that Q is high, Q dash is low. Q dash is low. Q dash is low. The capacitor is discharges like that, shown in figure. Here also like that here. Whenever the capacitor voltage reach to one-third VCC is nothing but trigger voltage. The capacitor is nothing but the trigger voltage. The trigger voltage is less than one-third VCC. That is output of the comparator 2 is high. Q is high. Q dash is low. Q dash is low. The transistor is driven into cutoff mode. Again, the capacitor charges like that. Whenever that Q dash is high, again the Q dash is high. The transistor QD is driven into cutoff mode, disconnected from that seventh pin. Again, the capacitor is charged through RA and RB resistances with the help of VCC. With the help of VCC, like that. The charging and discharging, like that. Here, during that T on period, the capacitor is charging. During the T off period, the capacitor is discharging. Charging time constant is greater than the discharging time constant because the charging of the capacitor through two resistance RA, RB. Therefore, the charging time constant is RA plus RB into C. The discharging time constant is less compared to charging time constant because the discharging of that capacitor through RB only. Therefore, the discharging time constant is RB into C. Due to that variations in charging and discharging time constants, a symmetrical rectangular wave, symmetrical rectangular wave is not generated. A symmetrical rectangular wave is generated like that. Duty cycle, here duty cycle is equal to duty cycle of the waveform is equal to T and by T Tn by T into 100. T is nothing but T is nothing but T on plus T off. T on plus T off. T on is nothing but width of the pulse, that is W by T into 100. This is the duty cycle of the waveform. Now derivation. Derivation here. Duty cycle derivation. Here F is equal to 1 by T. F is equal to 1 by T. Frequency of that waveform. During that the voltage across a capacitor in an RC circuit can be modeled by equation. One important point here is the voltage across a capacitor. The voltage across a capacitor in an RC circuit. In an RC circuit can be modeled by using the equation. By using equation is VC is equal to V final plus V initial minus V final into e power minus T by RC. V power T by RC. Here the capacitor is here. The capacitor voltage is like that. Two reference levels like that here. Two-third VCC, and this one is 1/3 VCC. The capacitor is charging through two resistances RA plus RB. The charging time constant is RA plus RB into C. Discharging time constant. The capacitor is discharged through RB resistance. Therefore, the time constant is RB into C. This is the charging. This one is a initial value. The capacitor voltage is reached to 2/3 VCC, and finally at steady state it is reached to VCC. According to equation, VC of T is equal to V final plus V initial minus V final e power minus T by RC. Here is VC is equal to V final is VCC. V initial is the capacitor charging from 1/3 VCC. 1/3 VCC minus V final is steady state value is VCC. This is the value at T is equal to 0. This is the value VCC value at T equal to infinity final. This value VC is equal to 2/3 VCC. 2/3 VCC. E power minus charging time. The amount of time will require to charge the capacitor, that is called as charging time, minus TC by RC. Minus TC by RC. 2/3 VCC is equal to VCC into VCC plus this one is 1/3 VCC minus 2/3 VCC into e power minus TC by RC. Here VC, this is 2/3 VCC is equal to VCC minus 2/3 VCC e power minus TC by RC. Interchanging these two. Here bring this side 2/3 VCC e power minus t by RC is equal to VCC minus 2/3 VCC. 2/3 VCC e power minus TC by RC. 1/3 3 VCC minus 2 VCC, that is 1 VCC by 3. This one 3 cancel. VCC is cancelled. Therefore, this one is 2 by e power TC by RC is equal to 1. Therefore, e power TC by RC is equal to 2. Apply logarithm on both sides here. Here apply logarithm. ln e power TC by RC is equal to ln 2. Therefore, TC by R into C is equal to ln into 2. That is R is nothing but RA plus RB. TC is equal to ln 2. R is nothing but RA plus RB. The capacitor charging through two resistances RA plus RB into C. ln 2 is equal to 0. TC is equal to 0.693. 0.693 into RA plus RB into C. This is the charging time constant. The amount of time will require to charge the capacitor value is the TC is equal to 0.693 RA plus RB into C. This is nothing but T on. This is nothing but T on. This one is charging. This one is discharging. 1/3 VCC. 2/3 VCC. Here discharge through RB resistances. The capacitor is discharge through RB resistance. Therefore, again we use VC is equal to V final, V initial minus V final e power minus t by RC. Here no need to use this. Generally, whenever the capacitor is discharges, this value 2/3 VCC into e power minus t by RC. VCC into VC of t is equal to VC of t. VC is equal to 2/3 VCC is the in the discharging mode. 2/3 VCC is the initial value of the capacitor. Generally, in discharge capacitor discharges, the expression is V naught into e power minus t by RC. Therefore, VC is equal to 2/3 VCC into e power minus t by RC. Therefore, VC is equal to the capacitor voltage is reached to 1/3 VCC. 1/3 VCC is equal to 2/3 VCC e power minus TD by R is RB into C. VCC is cancelled. 3 is cancelled. Therefore, 1 is equal to 2 by e power TD by RB into C. TD by RB into C. E power TD by RB into C is equal to 2. Apply the natural logarithm here. ln E TD by RB into C is equal to ln 2. Therefore, TD by RB into C is equal to ln 2. Therefore, discharging time constant TD is equal to discharging time ln 2 RB into C. ln 2 is 0.693 RB into C. 0.69 3 RB into C. This is T of. This one is T of 0.693 RB into C is nothing but TD. Total time in that waveform, a symmetrical waveform is generated because time constants are different here. This one is T on, this one is T off. Therefore, total time T is equal to T on plus T off. T is equal to T on time is we know that 0.693 RA plus RB into C. T of time is 0.693 RB into C. 0.693 C is common term. 0.693 into C is the common term. RA plus RB plus RB. Therefore, time period T is equal to 0.693 C RA plus 2 RB. RA plus 2 RB. Therefore, frequency of that waveform, a symmetrical waveform is F is equal to 1 by T, 1 by 0.693 RA plus 2 RB into C. Next, calculate duty cycle of the waveform. That is duty cycle D is equal to T on by T into 100. T on we know that charging case TC. T on is nothing but TC, that is 0.693 RA plus RB into C by total time T is 0.693 C RA plus 2 RB into 100 here. These are cancelled. CC is cancelled. Therefore, duty cycle is RA plus RB by RA plus 2RB into 100. This is the duty cycle of that waveform. Duty cycle of that waveform. With this, the analysis and derivation part is completed.